Okay, chapter 3 deals with number systems and whole number operations, addition, subtraction, multiplication, and division. So in this first section, we will talk a little bit about the origin of numbers and their representation in the number system, a couple different numeration systems, and place value in base 10. We're not really going to worry about other bases too much. So numerals, of course, are written symbols to represent cardinal numbers when you're counting an amount of things. Of course, our Hindu Arabic numbers are represented along the bottom, and you can see some different representations of these numbers in various historic cultures. The numbers that you will run across most often, of course, you will see Roman numerals. You'll occasionally see Greek numeration as well. And you're not going to be asked to memorize these. It's just an awareness of the different ways historically that numbers have been represented. So a numeration system is a collection of properties and symbols agreed upon to represent numbers systematically. So, of course, you've all seen tally marks. I think of like card games or dominoes when you would use tally marks to represent objects where you group. You have 4 vertical lines and then a slash to group the 5, and then you move on to the next grouping. So visually you can see the groups of 5, and so any tally marks that aren't grouped in 5s can just be added. So you've got 5, 10, and 3 more makes 13. Roman numerals are based upon these values. So I represents 1, V represents 5, X represents 10, L represents 50, and so on. So whenever you have this IV, since I is 5 and or is 1 and V is 5, then 1 before 5 means 5 minus 1, or 1 less than 5, or 4. So IX, since X represents 10, this means 1 less than 10, or 9. Now L represents 50. So again, if you put a smaller denomination before a larger denomination, you will be subtracting that quantity. So the 10, the X, is being subtracted from 50. So 50 minus 10, or 40. C represents 100 and X represents 10. So 10 before 100 means we're taking 10 from 100. D represents 500 and C represents 100. Again, when a smaller denomination is before a larger, you're subtracting it. All right, in our own Hindu Arabic numeration system, we know that we have 10 digits, 0 through 9. So all of our numbers are constructed from those digits. And the place value is based on powers of 10. So when you see 5,678, each one of those digits has a place value. So we start at the right with our units. 8 is a unit, 7 is tens, 6 is hundreds, and 5 is thousands. So if we expand, actually we've expanded a different number, 6,789. So remember, 6 means thousands, which is 6 times 10 to the third power. 10 to the third power is 1,000. Plus 7 is in the 100s place, so 7 times 10 squared, which is 100. Plus 8 is in the tens place, so 8 times 10. Plus 9 is in the ones place. 9 times 1. All right, if you have any number and it's multiplied several times, then we have a shorthand for that. A to the power of n simply means A is a factor n times. Now, as long as A is not equal to 0, we have another special rule that's very important to remember. A to the 0 power is equal to 1. It doesn't matter what value A is. Any number to the power of 0 is equal to 1 as long as A itself is not 0. When you are teaching mathematics, you will sometimes use base 10 blocks. So of course you have the single unit, which is a tiny little cube. You have a long, which represents 10 units. You have a flat, which represents a 10 by 10 or 100 units. And then, of course, you have a large block, which is a 100 by 100 by 100. It will contain 1,000 little blocks. So you can build numbers using these models. Now, sometimes we can write numbers in with different bases other than base 10. Of course, base 2 is a binary system which only contains 2 digits, 0 and 1. This is important because computer programs are designed in a binary system. Okay. So one of the 2 digits represents the presence of an electrical signal and the other by the absence. So 0 might mean a closed signal, and then 1 might mean an open signal. Now, when you are converting from a base 2 to a base 10, then you just have to remember that each place value is a power of 2. So you're starting from the right. You've got 1, 1, 1, 0, 1. So that first digit on the right is 2 to the 0 power, which is 1. Anything to the 0 power is 1. And then you've got the next one would be 2 to the first power, which is 2. Then 2 to the second power, which is 4. 2 to the third power, which is 8, and 2 to the fourth, which is 16. So we have one of those, 2 to the fourth, plus 0, 2 to the third, plus 1, 2 to the fourth, plus 1, 2 to the first, plus 1, 2 to the 0. So 2 to the fourth power, remember, means 4 2's multiplied together. 2 times 2 times 2 times 2 is 16. Plus 0, 2 to the third. It doesn't matter what 2 to the third is if I'm going to multiply it by 0. It would be 8, by the way. But 0 times anything is just 0. Okay. Plus, this should say 2 to the second power. Let me fix this. This right here should say 2 to the second power, plus 1 times 2 to the first power, plus 1 times 2 to the 0. So you're adding 16 plus 0 plus 4 plus 2 plus 1, which is 23. So if you wanted to convert 23 to base 2, it would be 10111 base 2. We're not going to spend a lot of time on base conversions in this course. All right, so we are going to move on to the next presentation. Okay, watching my time here. Okay, we're still in chapter 3. We're going to talk about comparing and ordering numbers. We're going to talk about various models of addition and properties of addition. addition algorithms, and how to use them to solve problems. We are not going to talk much about other bases other than 10, but we will talk a little bit about mental computations and estimation. Okay, this is a very common model for teaching addition of numbers. So you have set A, which has 4 blocks. You have set B, which has 3 blocks. And so you have 2 different circles for your sets. And then you have a circle where they come together in addition. So the number of things in set A is 4. The number of things in set B is 3. And when you put them all together, of course, the number in the union would just be 7. So this is a nice way to demonstrate addition. Okay, so we have no common things. We're just adding numbers of blocks. So if you're adding 2 disjoint finite sets, so 2 sets of things, and you don't have anything that's in both sets at the same time, then when you add, you just take the number of things in set A and the number of things in set B and put them together. You union them together. So that's all this is saying. Okay, another method for teaching addition is using a number line. Here we have Kenzo has 4 feet of red ribbon and 3 feet of white ribbon. How many feet of ribbon does he have altogether? And then another problem that we could model with a number line. One day, Laura drank 4 ounces of orange juice in the morning and 3 ounces at lunchtime. If she drank no other orange juice that day, how many ounces of orange juice did she drink for the entire day? So here we have the 4. So notice we start at 0 and go all the way to 4. And then at 4, we add the second arrow that's 3 units long, which goes all the way to 7. So using a number line where you put these arrows tip to end is another nice way to demonstrate addition. So this same model works for both problems, whether you're talking about ribbon or orange juice. So this is another great model for visualizing addition. Students need to understand that the sum represented by any 2 directed arrows can be found by placing the end point of the first directed arrow at 0 and then joining it to the directed arrow for the second number with no gaps or overlaps. So those are important things about number line models. So then, of course, you can simply read the sum of the numbers. Here's the definition of less than. For any whole numbers A and B, A is less than B, written, and then you see A with the symbol less than B. If and only if there exists a natural number K such that A plus K is equal to B. So we define less than in terms of addition. There's something we could add to A, a whole number, a natural number, to make it equal B. So therefore, A is less than B. Now, we know that if you have a line underneath your inequality, then it has a dual meaning. So this means that A is either less than B or it could possibly be equal to B. So if I said 5 is less than or equal to 7, that is true because it satisfies the first part. 5 is less than 7. If I said 5 is less than or equal to 5, that would also be true because it satisfies one of these conditions. 5 is equal to 5. Saying A is greater than B is the same as saying B is less than A. So we could simply turn the whole sentence around. And of course, that would have the same meaning. Okay, another way of showing addition is what is called counting on. So it's an addition strategy where addition is performed by counting on from one of the numbers. So if we were going to add 5 plus 3, then we would start at 5, and then maybe even using our fingers, we would put up one finger as we count 6, and then another finger as we count 7, and then a third finger when we count 8. So we see that we've added 3 additional numbers to 5, and we ended up with 8. If we wanted to add 7 plus 4, we would start at 7, and then again, using 4 fingers to count on 8, 9, 10, and 11 as we add an additional finger each time. So we know when we've added 4 numbers and we get to 11. So we know that 7 plus 4 is 11. So that's just a way, it's called counting on. So another way of demonstrating addition. Teaching doubles is important for young students because this can add an additional strategy for adding. So 3 plus 3, 4 plus 4, 5 plus 5, those are all important concepts to teach students to recall quickly. So after they've mastered doubles, they can do doubles plus 1, doubles plus 2, and so on. So for example, if a student already knows that 6 plus 6 is 12, then when they want to add 6 plus 7, they know that that's doubling 6 plus 6, and then just adding an additional 1. So the associative property is used to demonstrate why this works. Of course, 6 plus 7 can be written as 6 plus, and then 7 could be written as 6 plus 1. If we just shift the parentheses to the left, which is what happens when you use the associative property, you could think, all right, I already know 6 plus 6 is 12. I'm just adding an additional 1. So this would be doubles plus 1. So 1 more than the double of 6 is 12 plus 1, or 13. Sometimes you kind of have to pause one of these models and just kind of think through it for a moment before it kind of grasps on in your brain. I had to do that myself, being as I don't normally teach elementary students how to add. So these were really interesting concepts. All right, another way you can teach children to add is making of 10 and then adding on any remaining amount. Okay. It's not showing how you would do that. So let me give you a little demonstration. So let me go back to my pen. Let's say I wanted to add 7 plus 6. Well, I know that 7 plus 3 is 10. So I could think, okay, 7 plus 3 is 10. I know that. But the 3 from the 6 would leave 3 more to add. So I can't just add 3 and stop. I know that 3 plus 3 makes the 6. So I can say, okay, 7 plus 3 is 10. And then I know there's going to be 3 more after that. And so 7 plus 6 is 13. So that's what's called making 10, where you try to figure out how much of that number do I need to make 10 and how many will be left over. So that's another great strategy for adding. It even works if you get up to numbers like, let's say you were going to add 77 plus 6. Okay, again, you could think of the same strategy. I know that if I take 77 and just add 3 more, then again, pardon my trying to make 7s with a line through it so they don't look like 1s. I know that if I could just add 3 more, that would get me to 80. So that would be great. But then I still need 3 more after that. So 77 plus 3, I know is going to get me up to 80, but then I'll still have 3 more to add on. And so I can get to 83. So the making of tens is another great addition strategy that you can utilize. Okay, let's talk about some properties of whole numbers. We have a property that is called closure property of addition of whole numbers. This simply means that if I add any two whole numbers, then I'm going to get a unique number that is also a whole number. Now, let me remind you of what the whole numbers are. The whole numbers are the set of numbers that start at 0 and then include the natural numbers 0, 1, 2, 3, and so on. The group of whole numbers does not deal with any fractions or any decimals. Of course, this would be for your basic elementary students when they're beginning to learn to add and subtract. You won't be talking about fractions or decimals too much at first. So the group of whole numbers is where you begin. And the group of whole numbers we say is closed under addition because I know if I add any two whole numbers, I'm going to get a unique answer that will also be a whole number. So if you think of it as closed, I like to think of it like this. You don't have to go outside of the group to find your answer. And we'll look at some instances later, some things that are not closed under certain operations. For example, subtraction is not closed under the group of whole numbers because if I wanted to subtract 2 minus 3, well, 2 minus 3 is a negative number. I would have to go outside of the group of whole numbers to get the answer, which is actually -1. And so we'll look at some things that are not closed. But addition is closed under the whole numbers. Okay. The closure property implies that the sum of two whole numbers exists and that it is a unique whole number. So the fact that it exists, it is unique, and it is within the set of numbers are all important concepts of closure. So here's an example. Of course, 5 plus 2 is a unique whole number, 7. We didn't have to go outside of the group of whole numbers to get our answer. Another important property of numbers is called the commutative property. And by the way, the names of these properties and how they work are important, so you will want to make note of these. The commutative property simply means that the order in which you add two numbers is not important. If you want to add 3 plus 5, it's the same as adding 5 plus 3. So we've demonstrated this with a line graph. In the first, on top of the number line, we started with the number 3 and we added 5. And we see that we ended up at the number 8. Below the number line, we started with the number 5 and we added 3, and we see that we still end up at 8. This idea is called the commutative property. It has also been demonstrated with blocks here, one block representing a unit of 3 and the other block representing a unit of 5. And you can see how it doesn't matter if you do the 3 and then the 5 or the 5 and then the 3, you get the same length. So this is a very geometric approach to showing the commutative property. The associative property is another thing that you need to understand. And think of this word associative. The root word is associate. What numbers are associated with the others. And this will always happen when you're adding more than two things. So we're adding three things, A and B and C. I want you to notice, this is very important, that each side of the equal sign has the numbers or the letters, as it were, in the same order, ABC, ABC. We are not moving the numbers. The only thing that's moved are the parentheses. On the left half of the equal sign, we have grouped or associated A plus B. On the right side of the equal sign, we have grouped or associated B plus C. And all that would do is determine what you're adding first. Order of operations always says do what's in parentheses first. So let's say, for example, that I wanted to add 5 plus 2 plus 1. If I associate these numbers like I have them on the left side, I would first do what's in parentheses and add 5 plus 2, and I would get 7. And then I would add the 1, and I would get 8. On the right side, again, I'm writing the numbers in the same order, 5 plus 2 plus 1. The only difference is I've moved the parentheses to be around the 2 plus 1. That means that's what you do first, okay? So I'm going to add 2 plus 1 and get 3. Then I will add 5 plus 3 and get 8. So the associative property says you can, if you're adding 3 numbers, you can add the first 2 and then the third, or the last 2 and then the first, and you'll get the same thing. The important thing to note is that the associative property is not saying move the numbers. The associative property is saying you can move the parentheses. The identity property simply says that there is a unique whole number that when you add it to any number, you will get the identical thing that you started with. And you can also add it in any order. So given any number, we're going to call it A plus 0 is identically what you started with, A. Also, 0 plus A is A. So it doesn't matter if you add 0 on the right side or the left side, you get the identical number that you started with. That's how I like to think of identity. So 0 is the additive identity. All right, let's see if we can test our skills. It says, which properties of whole numbers are illustrated in each of the following statements? If you want, you could pause this video and see if you can guess. Do we have the commutative property demonstrated? The associative property? Do we have closure? Or do we have additive identity? Let's take a look. Part A says 6 plus 8 is equal to 8 plus 6. Did you correctly identify that as the commutative property of addition? Remember, the commutative property says when you're adding 2 numbers, the order does not matter. 6 plus 8 is the same as 8 plus 6. Part B says that 1001 plus 834 is a unique whole number. Did you guess that that was the closure property of addition? Remember, the closure property of addition simply says that when you add 2 whole numbers, you're going to get another unique whole number. You won't have to venture outside of the whole numbers to find the answer. All right, we're starting to get a little more complicated with parentheses and such. Have the parentheses moved in part C? No. The left side of the equation has the parentheses around the first 2 numbers. The right side of the equation has the parenthesis around the first 2 numbers as well. That's how I know this is not the associative property. The only thing that's happened is the 3 and the 6 have changed places to be 6 plus 3. And that sounds like the commutative property. So this is representing the commutative property. Now, in the next one, On the left side of the equation, we have 8 plus 5 plus 2. And then it's been switched to plus 8 plus 5. That is definitely the commutative property when you simply switch the two things you're adding. Then what has happened from this equal sign, the first equal sign, to the second equal sign is the parentheses have moved from the 8 and the 5 to the 2 and the 8. So the first part is the commutative property, and the second part is the associative property. So remember, when the numbers move, that's called the commutative property. When the parentheses move, that's called the associative property. Okay, so here is a great demonstration for a concrete model for adding numbers. So we have 14 represented by one long. Remember that a long string of blocks represents the number 10. So we have one of those and then four. I'm trying to figure out where my pointer is. There it is. So we have one long string of blocks represented 10 and then four more to represent 14. And then in the other circle, we have 23 represented by two 10s and three 1s. So when you add them together, you can simply bring the blocks into the union circle. So you see that you have three longs and 1, 2, 3, 4, 5, 6, 7 little blocks or 7 units. So of course that's three 10s and 7 units, which represents 37. So it's a great way to model addition of two-digit numbers using your longs and your units. An expanded algorithm here. So you're adding the 4 plus 3 is 7. And then you're adding, you have to think of this as 10 and 20, which gives you 30. So you can add your 7 and 30 to get 37. Now, of course, the standard algorithm that many of us grew up with is simply to add 4 plus 3 is 7 and 1 plus 2 is 3, which works nicely if we don't have to so-called carry the 1 or anything like that. But giving students options and letting them see addition in many different ways really helps them to wrap their brain around exactly what is happening. Okay, so here's what happens when you have a so-called carrying situation. So we know that when you add 7 plus 8, you get 15. So you add your ones, and then you add your 10s, 30 plus 20 is 50. And so then, of course, we add 5 plus 0 is 5, and 1 plus 5 is 6. So that works out nicely. All right. If you were adding this using the standard algorithm, you would do this so-called carrier 1. They call it regrouping. So 7 plus 8 is 15. So your 10 comes up here and your unit stays here as a 5. So we have 3 plus 2 is 5 plus 1 more is 6. So you'll be hard-pressed to find an elementary school teacher that still calls this carrying the 1. They like to think of this as regrouping. So you have 15, so you put your 1s and then you regroup your 10s in the 10s column. Okay, so here we're showing addition of three-digit numbers with a model. So if we're adding 186, so we have, remember that this represents the big flat represents 100. Of course, 80 would be 8 10s, and then you would have your 6 units. And then you have 127. But you have to group your units. You have more than 10 units. You can take 10 of those tiny little cubes and then replace it with a long.
And so that's a way of showing your regrouping when you're adding 186 and 127. And after you regroup, you're only going to be left with 3 units. Okay? And then you've got your 1 long. But we have more than 10 longs. So we take 10 of our longs and replace it with a flat. So now we know we have an additional 100. And we're only left with 1 solitary long. So that goes in the tens place. And then we can add our flats together. So you end up with 3 flats representing 3 100s, 1 long, and then 3 little cubes. So it's a great way to demonstrate regrouping with addition of 3-digit numbers. Okay, we can also use partial sums from left to right. So in partial sums, you would start with your leftmost digits. So remember, these are in the hundreds place. So you add 500 plus 700 to get 1200. Then you add your tens place. So you've got 60 plus 50 is 110. And then you can add your units. 8 plus 7 is 15. And then, of course, you can add traditionally your columns and end up with 1,325. I like this partial sums method. All right, in the lattice algorithm, every digit is kind of sliced in 2 along the diagonal. So when you add 7 plus 8, you get 15. So you put the 1 in the top triangle and the 5 in the bottom triangle. 6 plus 7 is 13, so you put the numbers in there similarly. 5 plus 6 is 11, and 5 plus 3 is 8, so that's 0, 8. So when you go to do your answer, so you think of this kind of on the diagonal. So this is your 5. 3 plus 1 is 4. 1 plus 1 is 2. 8 plus 1 is 9. And then, of course, you won't need to put anything there since that's 0. But if it was something other than 0, that would be your next digit to the left. That's called the lattice algorithm. In the column addition algorithm, we add numbers in each column, writing each sum directly beneath the column. And then we regroup each place 1 column at a time. So base 10 blocks are often used to demonstrate column addition. Okay. Opposite change algorithm. So we decide which addend is closer to a nice number, typically 10 or a multiple of 10. And then we decide how to adjust the addend so that it ends up in 1 or more zeros, and adjust the other addend in the opposite direction. So the goal is to make the addition problem a problem without the need to regroup. Okay, so in this one, again, that's kind of like making 10 would be the closest thing that I could say about that one. Mental math, of course, and computational estimation are very important. It really, really helps students if they can have some mental math strategies and ways to estimate. It helps them to know if their answer makes sense. Is it reasonable? Or did I make some huge error? So it's really important for students to learn how to estimate a reasonable answer. Okay, so here a way to add from the left. Of course, we've got 70 plus 20 equals 90, and then 6 plus 5 is 11. And so that's very similar to the partial sums. 90 plus 11 is 101. All right, if we wanted to add this by breaking up and bridging, we could take 20 of the 25 because it's easy to add 76 and 20. That's just 96. And then we would take the additional 5 and add that on to the 96 in the end. So again, it's not about one of these ways being better than the other. Just sometimes a particular problem might lend itself nicely to one particular strategy over another. But a lot of times it's also just a matter of choice. What makes sense to each individual student? Okay, here's a fun way to do addition, trading off. I know that if I can just add 4 to 8 to 476, that'll get me up to 80. And then whatever number you add to your first number, you subtract that from your second number. So if I take the 4 that I added with 76 and subtract that from the 25, I'm going to get 21. So then 80 plus 21 becomes significantly easier to add mentally. I just add 8 plus 2 to get the 10. And then, of course, I've got the additional 1. So again, these are mental math strategies to teach students. Compatible numbers are numbers whose sums are easy to calculate mentally. So let's say I wanted to add 130 plus 50 plus 70 plus 20 plus 50. You could group these because of the commutative property. You could arrange these any way you like. So notice they've grouped 130 and 70 because that's easy to see that adds to 200. And then 50 plus 50 adds to 100. So we have 200 plus 100, and then the only number we didn't pair up with anything was this 20. So we know we have 320. So that's a great way as well to teach mental addition. Here we can make compatible numbers. I see that I'm adding 75 plus 25, which is 100. But there was an additional 1. If I said 75 plus 25, remember that was 76. So then I can just take that little 1 I ignored earlier and add it to the end. Okay, so let's talk a little bit about estimation. We can see that if you add 39 and 64, that's roughly 100. 23, 32, and 49 is also roughly 100. So we can estimate the sum to be approximately 200. So that way, if we add these up and we get something, grossly off the mark, maybe we get something close to the thousands, we know we've probably made an error in our place value or something. And we all make errors, so it's nice to know a way to stop and say, wait a minute, that doesn't make sense. There's no way these numbers could add up to the answer that I got. Okay, clustering is another nice way to estimate whenever you have a group of numbers that are clustering around a common value. So let's say you wanted to add these numbers. I can see how, especially as an elementary student, but well, heck, as anybody, if I had to add these up without a calculator, I'd have a big sigh first. But we can at least estimate this sum because all of these numbers are hovering in the 5,000 range. So I could at least estimate that I'm adding somewhere in the neighborhood of 5,000 5 times. So I could multiply 5 times 5,000 and say, well, this is roughly 25,000. You could, of course, simply round. Here we're rounding to the nearest thousands. So 7,262 rounds down to 7,000. 3,806 rounds up to 4,000. And so when we subtract, we get somewhere in the neighborhood of 3,000. I like the range method. So if we round both numbers down, we get 7,000 and 3,000, which adds to 10,000. If we round both up, we get 8,000 and 4,000. So this is a great way to say, okay, the answer to the real problem must lie somewhere between my low estimate and my high estimate. Okay, so we are going to move on to the next PowerPoint. See how much of this we can get accomplished today in the time allowed. All right, we're going to talk a little bit about subtraction algorithms and the relationship between addition and subtraction. And we'll also talk more about those mental computation skills and estimation. So this is going to go hand in hand, very similar to the addition. The takeaway model, where you have a set of objects. Say you wanted to do 8 minus 5. You have 8 objects and you take away 5 of them. So that works really nicely. In the number line model, subtraction is represented by moving left on the number line after a given number. So here's the takeaway model. You see you have 8. Here we're taking away 3, which leaves 5. Here we have 5. And then to subtract, we simply draw an arrow from 5 going the opposite direction. And so we see that we end up at 2. So 5 minus 3 is 2. The missing addend, this can be thought of as the number of blocks that must be added to 3 in order to get 8. So the number 8 minus 3 is missing 3 plus what is 8. So thinking of subtraction in terms of addition is helpful for many students. All right, you see that you could model this missing addend with your little sets of blocks. 3 plus how many more do we need to equal 8? Or on a number line, okay, you have 3 plus what is equal to 8. So you could simply count on the number line all the way from 3 to 8 to find out that the answer is 5. Okay, so the definition of subtraction for any whole numbers a and b, such that a is greater than or equal to b. A minus b is the unique whole number c such that b plus c is equal to a. So again, this is defining subtraction in terms of addition, similar to what we said. Now, it's really important that a is greater than or equal to b so that we're not trying to subtract a larger number from a smaller number. And the reason that's important is because, remember, we're still just talking about whole numbers. We have not talked about negative integers at this point. All right, subtraction can also be thought of as a difference when you're comparing. If you have Juan has 8 blocks and Susan has 3, the difference is 5. So it's a great model of subtraction as well. All right, it can be shown that if A is less than B, A minus B is not meaningful in the set of whole numbers. Therefore, subtraction is not closed on the set of whole numbers. I mentioned this earlier. So if you have 5 minus 8, that is not a whole number. And that's why subtraction is not closed in the whole number set. It could be closed if we talked about integers, but not in the set of whole numbers. All right, introducing algebra with symbols like here we have the sun, and then we have this diamond shape. These are great ways to start introducing algebra at an early age. So 9 plus 5 is equal to the sun. So you can find that the sun is equal to 14. So showing them that variables represent unknown quantities. So for example, if the sun is equal to 10, then 10 plus 5 equals the sun is a false statement. And if the diamond is equal to 8, then 12 minus 8 equals 4 is true. We know that solutions to algebraic equations are those values which make the math sentence true. So that's what we call a solution to an equation. Okay, so we'll try to go through these algorithms fairly quickly. They're going to work very similar. If you have 243 and you want to subtract 61, you can demonstrate this with a concrete model. See, we have the 200 flats, or the two flats that represent 200. We have 4 longs representing 40, and then we have 3, and we're trying to take away 61. Now, taking away 1 is not difficult, but we can't take away 60 because we don't have 6 longs. So we'll have to break up and trade. We'll have to trade this flat for 10 longs, okay? So now that we can take away 6 longs and 1 unit, and that will leave us with 182. So 1 flat is 100. It will leave us with 8 longs and then 2 little blocks. Okay, so now we take away the 61 and you can see that better. All right, so there's your 182. Okay, equal additions. The equal additions algorithm for subtraction, it's based on the fact that the difference between two numbers does not change if we add the same amount to both numbers. So if you were subtracting 255 minus 163, if you added 7 to both numbers, you would be subtracting 170, and that might be easier. You could go ahead and add another 30, and you would be subtracting 292 minus 200. And again, that's going to be the same as the original problem. Okay, so equal additions. Add the same number to both numbers and then perform your subtraction when you get numbers that are nice and easy to subtract. Great strategy. Okay, counting up algorithm is best described as making change. So it's the way that, cashiers and tellers used to, give you your change back by starting with the amount and working their way up to what you gave them. It's kind of a lost art, of course. So for example, if you're subtracting 100 minus 31, you could think, okay, I'm going to start with the 31 and I'm going to add up to 100. So I know if I add 9 to 31, that gives me 40. And then 60 more would give me 100. So the 9 and the 60 that I added, 69 would be the answer to the subtraction problem. Another great strategy for subtraction. It's called the counting up algorithm. Noah owed $11 for his groceries and he used a $50 bill to pay. While handing Noah the change, the cashier said 11, 12, 13, 14, 15, 20, 30, and 50. How much change did Noah receive? So when the cashier said 11, that meant that's how much money Noah had started with. So the cashier had not started giving him money. And then as the cashier counted up, 12, that he gave him $1. 13, another $1. 14, another $1. 15, another $1. But then he skipped to 20, so he must have given him a 5. Then he skipped to 30, so he must have given him a 10. And then he went from 30 to 50, so that was a 20. So you can see that the change he gave back was $39. Okay, trying to find my clicker. And there it is added up for you. So counting up. People don't give change back like they used to because it just tells them on their little computer screen exactly what change to give you. So they don't have to think about it so much. All right, mental computation, breaking up and bridging. So if I want to take 74 and subtract 26, I could first subtract the 20. It's easy to subtract 20 from 74 because I just get 54. And then I could subtract the 6 and get 48. So breaking up and bridging is what that would be called, to mentally subtract 74 minus 26. Great strategies to teach kids. Trading off. So again, we add the same number to each one. So if I add 4 to 74 and 26, that makes 26 now 30, and 74 is 78. So it's easy to subtract mentally 78 minus 30 and get 48. Dropping the zeros, 7,400 minus 600. So again, just think 74 minus 6, and then put your 2 zeros back on in the end. All right, I think I have one more PowerPoint. Actually, a couple more. Let's see what we can get in. I am watching the time. I don't think we'll finish this one, but that's okay. Let's talk a little bit about multiplication now that we've discussed addition and subtraction. Of course, one of the simple ways to think about multiplication is simply repeated addition. Also, we could use a little geometry with an array or an area model. We could also think of multiplication as a Cartesian product. So let's look at repeated addition. Suppose we wanted to multiply 4 times 3. So we could think of that as being addition of 4 threes. So 3 plus 3 plus 3 plus 3, 4 times would equal 12. So that's the repeated addition model for multiplication. All right, here's another 5 times 4. If you have 5 4s together, again, you could use geometric blocks to show that that would be 2 10s or 20. 5 times 4. Here's showing the repeated addition on a number line. So I've added 5 4s just by starting at 0 and making a 4-unit arrow 5 times, and that leads me to end up at 20. So of course, when you are teaching these operations, you're going to want to vary up your strategies so that you show as many different ways as you can. So remember, n times a simply means you're multiplying or you're adding a n times. So that's the reason this repeated addition model works. Here's an array. So we have 4 lines intersected by 5 lines. So you can simply count the number of intersections. So that's a great way to demonstrate multiplication. Or simply algebraically, we have a 4 by 5 rectangle. And so if you count all of the little squares, you'll find that that's 20 squares. And that's why we would say if we were multiplying 4 units by 5 units, we would get 20 square units if we were finding the area of that rectangle. So great models for multiplication. Okay, so Cartesian product is also a type of multiplication, which we kind of talked about before when we were looking at sets. So this talks about a situation where you can take either world history or ancient history. And for your second course, you can take a foreign language, Latin, French, or German. So we could use a tree diagram, as we've done before, to demonstrate the different ways. So we'll let H represent the history courses we have to choose from. There are 2 of them. And L represent our foreign languages. So here's a tree diagram showing what the different combinations. So notice the schedule first breaks into 2 branches, one for world history and one for ancient history. And then each of those branches out into 3 branches, Latin, German, French, or Latin, German, French. And so then the different combination or the different paths that you could follow, world history Latin, world history German, world history French, ancient history Latin, ancient history German, ancient history French, are all the combinations. So yes, this is a type of multiplication. The fundamental counting principle tells us that there are 6 ways, all right, 2 different histories to choose from, 3 different languages, and 2 times 3 is 6. All right, and we can really formalize that here. If we have finite sets, so sets that can be counted, if the number of things in set A is little a, and the number of things in set B is little b, then A times B is the number of things in the Cartesian product of A times B. That's how many ways we can pair up the elements in A and B. So in this alternate definition, sets A and B do not have to be disjoint. The expression A times B can be just written as AB. It simply means the product of A and B. A and B are called factors. When 2 things are multiplied together, they are factors. All right, so talking about the closure property, we learned that the set of whole numbers is closed under addition. It is not closed under subtraction, but it is closed under multiplication. If you multiply any 2 whole numbers, you're always going to get another unique whole number. Again, you don't have to go outside of the whole number set in order to find your answer to a multiplication problem of whole numbers. The commutative property of whole numbers holds for multiplication as well. The order in which you multiply does not matter. A times B is the same as B times A. Think of 3 times 2, which is 6, of course, is the same as 2 times 3, which is 6. We failed to mention the commutative property when we talked about subtraction, because subtraction does not have the commutative property. When you change the order of a subtraction problem, you do not get the same answer. 8 minus 3 and 3 minus 8 are certainly not the same. The associative property also is true for multiplication as well as addition, not for subtraction, however. Again, notice that the parentheses have been moved. A times B in parentheses times C is equal to A times B times C in parentheses. So again, if you're multiplying more than 2 things, the order does not matter. We had the identity property for addition, and the identity element for addition is 0, because when you add 0 to a number, you get the identical thing you started with. For multiplication, we also have the identity property. However, the identity for multiplication is 1, not 0. When you multiply a number times 1, you get the identical thing that you started with. So think of identity in that way. All right, so we also have this idea of this 0 property for whole numbers. It simply means when you multiply 0 times any whole number, you always get 0. And it doesn't matter if you multiply by 0 on the right, A times 0, or on the left, 0 times A it's always 0. Okay, here's a demonstration of why the commutative property of multiplication holds. You can see these two rectangles, 3 by 5 and a 5 by 3, do have the same area. The associative property of multiplication is also true. I love these 3 different models. So if we are multiplying 3 times 5 times 4, we can think about multiplying 5 times 4 and getting this 5 by 4 rectangle. And we could think of 3 of those such rectangles. So we can think 3 times 20. Or we could group 3 and 5 together. 3 times 5 is 15. So we get this rectangle, a 3 by 5 rectangle. And we have 4 such rectangles. So 4 times 15 is also 60. In the last model, we have 3 times 5 times 4 is equal to 3 times 5 times 4, just showing that if you squish those first 3 blocks together, or if you squish these second 4 together, you're going to get the same 3 by 5 by 4 rectangular prism. And we'll all have the same volume of 60 little cubic units. All right, this is a nice way to show the distributive property. If you're multiplying 5 times 3 plus 4, so we have a 3 by 5 and a 4 by 5 and bringing those together as an addition problem. It's the same as taking 3 times 5 and 4 times 5 and then adding them together in the end. So here's a model for showing the distributive property of multiplication over addition. Okay, here is a formal definition of the distributive property. A times B plus C is equal to A times B plus A times C. So you multiply this times each of the terms in the parentheses. It works for subtraction as well. Okay, A times B minus C is A times B and A times C, and then subtract them. Because the commutative property of multiplication of whole number holds, the distributive property of multiplication over addition can be written in this way. So instead of putting the A on the left side of the parentheses, you could put the A on the right side of the parentheses, and it means the same thing, A times B plus A times C. But they've written it B times A and C times A, but remember, that's the same thing. Multiplication is commutative. So I could write B times A as A times B, and I could write C times A as A times C. So those are equivalent. We could generalize the distributive property for more than 2 things. So if you had 3 terms added together in a set of parentheses, so that would simply mean that A is multiplied times each one, and then you add up those products, A times B plus A times C plus A times D. Okay. When you reverse the distributive property, this is called factoring. Okay, so if you find a common factor in your 2 terms and bring it outside of the parentheses, we call that factoring. Bringing out a common factor. The factors of AB plus AC are A and B times C, because those are the 2 things that you could multiply together to equal AB plus AC. All right, here's an area model that we can use to show how we could multiply these 2 binomials. So x plus y represents this side of the rectangle, and z plus w represents this side. So each little rectangle is a product of the length and width. So x times z, x times w, y times z, and y times w, and then you just add up all the areas. So I like to think of it like this. The x is going to multiply times both terms in the second set of parentheses. The y is also going to multiply times both terms in the second parentheses. All right. So here they're just showing it in a little different way. They're showing that x plus y is going to be multiplied times x, and also x plus y is going to be multiplied by w, and then they're doing the distributive property. So this is just a different way of looking at the same thing we did on the previous screen. Okay. So it's very rich to show different ways to think of these different properties. Let's talk about a to the power of n, an exponent. Then when you have an exponent, the number that has the exponent is called the base. All right, that's called the base. B-A-S-E. Trying to write with my mouse pad again. And then the little superscript here is called the exponent. And it simply means that that's the number of times the base is multiplied by itself. So that's the exponent. So a to the power of n simply means we're multiplying a times itself n times. So a to the power of 3 would be a times a times a. And of course, a to the first power, or any number to the first power, is just that number itself. Okay, some other properties of exponents. This is kind of interesting. When you multiply a to the power of m times a to the power of n, you get a to the power of m plus n. And when you have a power to a power, a to the power of m to the power of n, you multiply powers in this case. So these are very important properties of exponents for you to remember. Okay. If you have a to the power of n times b to the power of n, you might write it like this. This indicates that anything in the set of parentheses has the exponent of n. All right, we talked about when you multiply like bases, you would add your exponents. When you divide with like bases, you would subtract your exponents. Okay, so we're going to practice our exponent skills here. It says write each of the following with one exponent. All right, so the first thing that we can do is rewrite 8 as 2 to the third power. Where's my pen? Oops, wrong one. There we go. 8 can be written as 2 times 2 times 2. And 16 can be written as 2 to the fourth. 2 times 2 times 2 times 2. So then we can multiply 3 times 5 and 4 times 3 to get 15 and 12. Now we have these like bases and we're multiplying, so we will add our exponents together and get 2 to the power of 33. All right, here is a model of multiplying 13 times 3. So we've taken a long representing 10 and 3 units representing 3 and just modeled that 3 times and then grouped them together. So of course the 3 tens make 30. The 9 units make 9. So we can see from the blocks that 13 times 3 is 39. All right. To multiply by 10, we can replace each piece with a base 10 piece that represents the next higher power of 10. We could replace a unit with a long or a long with a flat. So say we wanted to multiply 23 times 10. Well, we could take the two longs and turn them into flats. So the 20 becomes 200. We could take the 3 units and model those with tens. So now we've got 230. So this is a great way to model multiplication by 10. Okay, we could think of multiplication in an expanded format. So we know that if we want to expand 367, that's 3 100s or 3 times 10 squared plus 6 times 10 plus 7. So then we could just say, okay, we're multiplying 4 times 3 for our hundreds, which is our 1200. We're multiplying 4 times 6 for our tens, and 4 times 6 is 24. So 24 tens is 240. And then we're multiplying 4 times our 7 units, which gives us 28. So we could add 28, 240, and 1200 to get our final answer of 1468. All right. The lattice method, 23 times 14. So we create this square with the similar diagonals that we used in addition. And then we multiply the rows and columns. So I'm going to multiply first the column of 1 and the row of 2. And then, of course, that's going to go in this place here in the top left. That's 0, 0, 2. And then I do 2 times 4, which is 8. And then 1 times 3. So you multiply each row and each column. 1 times 3 is 3, so 0, 3. And then finally 4 times 3 is 12. So then you're just going to, the lattice model is always about the diagonals. So then this one is a 2, and then you're going to add these numbers. 8 plus 1 plus 3 is 12. So I put the 2 and I regroup, carry the 1 up here. So that's why there's a 1 right here. And then you add your 1, 0, 2, and 0, which is 3. And then if there was a number here, you would have that number. So the answer is 322. So that's the lattice method of multiplication. Some people really like that. All right, front end multiplication. All right, so you would multiply your 70 times 4, which is 280, and then 8 times 4 and get 32, and then you could just add the 2 together. 280 plus 32 is 312. We could use compatible numbers. If you're multiplying lots of stuff together, 2 times 8 times 5 times 40 times 5. Remember, multiplication has those great commutative and associative properties. You could do this in any order you like. So you might notice that, okay, if I multiply 2 times 5, that's going to give me 10. And if I multiply 40 times 5, that's going to give me 200. And that leaves 8. So I know multiplying 10 times 200 is just 2,000, and 2,000 times 8 is 16,000. So it's a great strategy for multiplication as well. I love thinking about money. So if I have to multiply something times 25, I'm thinking of it as quarters. So if I have 84 quarters, that's $21 or 2,100 cents. Front end estimation. So I could take 474 times 9. I could start by multiplying 400 times 9, then 70 times 9, and add the two numbers together. And I think I didn't quite finish that problem, but our time is up. So we will pick up with division next week. Thank you so much.